Welcome to Ultimate Sleep Doctor. Tonight we'll journey far, far away. Consider the vastness of space, a swirling galaxy of light and dust. The Milky Way, our home, is a breathtaking spectacle. Billions of stars born, lived, and now fading into the darkness. It's a humbling reminder of our place within the universe's grand design. To understand this incredible formation, let's explore the science behind its beauty. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift. Let's begin. The heart of our Milky Way galaxy, the galactic nucleus, isn't a quiet, empty space. It's a zone of incredible density, a swirling vortex of stars, gas, and dust. And at its very center sits something truly astonishing, a supermassive black hole, often designated Sagittarius A, but a mystery nonetheless. Understanding how these behemoths, with masses millions or even billions of times that of our Sun, came to exist within the nuclei of galaxies like ours is one of the biggest puzzles in modern astrophysics. The prevailing theory, and one that's gaining increasing support through observations and simulations, revolves around a process called seed black holes and their subsequent growth over cosmic timescales. Initially, the earliest galaxies weren't the grand spirals we see today. They were smaller, more irregular, and far more chaotic. Within these nascent galaxies, the first supermassive black holes likely emerged from the gravitational collapse of extremely dense, massive stars. Stars far larger and more short-lived than our own Sun. These stars, reaching the ends of their incredibly brief lives, would have undergone spectacular core collapse supernovae, releasing unimaginable amounts of energy and heavy elements into the surrounding interstellar medium. The sheer force of this explosion could have, under certain conditions, concentrated enough matter to trigger the formation of a microscopic black hole, perhaps a few tens or hundreds of times the mass of the Sun. Now, these initial black holes weren't sitting still. They existed within a rich environment of gas and dust, constantly being fed by this material. This accretion, the gradual accumulation of matter onto the black hole, is the key to their growth. As gas and dust spiraled inwards, drawn in by the black hole's immense gravitational pull, they heated up to incredible temperatures, emitting vast amounts of energy across the electromagnetic spectrum, radio waves, visible light, X-rays, and gamma rays. These emissions are how we can detect and study these distant, invisible objects. The rate at which a black hole grows depends on several factors, primarily the availability of fuel and the efficiency of the accretion process. If a black hole sits in a relatively sparse environment, its growth will be slow. However, in a galaxy with a dense gas disk, the accretion rate can be incredibly rapid. Furthermore, the black hole itself influences the surrounding environment, actively pulling in matter and compressing it, which then leads to even more heating and accretion. It's a self-sustaining process, a feedback loop driving exponential growth. One fascinating aspect of this process is the role of mergers. Galaxies frequently collide and merge over billions of years. When two galaxies combine, their black holes also come into contact. These mergers don't just combine the black holes' masses, they also release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time, predicted by Einstein's theory of general relativity. These mergers are thought to be a significant driver of black hole growth, particularly in the early universe when galaxies were more frequently colliding. It's important to note that the exact mechanisms and timing of supermassive black hole formation are still being actively investigated. There are several competing models, and the relative contribution of each process, seed black holes, mergers, and direct collapse, is still a topic of intense research. Some simulations suggest that, in certain environments, a black hole could directly collapse from a massive gas cloud, bypassing the need for a supernova. This direct collapse scenario is particularly relevant in the early universe, where the conditions might have been different. The growth of supermassive black holes wasn't a linear process. There were likely periods of rapid growth, punctuated by periods of relative stagnation. Perhaps a black hole would consume a huge amount of gas for a few 100 million years, then gradually slow down as the available fuel diminished. Or perhaps the black hole's activity would be suppressed by feedback mechanisms, powerful jets of particle shooting out from the poles of the black hole, which would heat and disperse the surrounding gas. The masses of supermassive black holes we observe today suggest that they've been growing for a very long time, at least 10 billion years. This implies that they formed in the early universe and have been steadily accumulating matter ever since. However, the details of this long, drawn-out growth story are still shrouded in complexity. Recent research is focusing on detailed simulations, using powerful supercomputers to model the evolution of galaxies and black holes over cosmic time. Furthermore, the distribution of supermassive black holes across the universe is somewhat puzzling. They tend to reside at the centers of most large galaxies, but there are also some isolated black holes that don't seem to be associated with any particular galaxy. Understanding this distribution will provide crucial clues about the processes that govern their formation and evolution. It's plausible that some black holes formed in smaller, less structured environments before galaxies even began to form. The Sagittarius A black hole at the center of our Milky Way is a particularly intriguing case. Its relatively small mass, about 4.1 million times the mass of the Sun, suggests that it may have formed relatively recently, perhaps just a few billion years ago. This contrasts with the older, more massive black holes found at the centers of other galaxies, leading to the hypothesis that our galaxy's black hole formed after a period of galactic evolution. Ongoing observations and detailed studies of its accretion disk are helping astronomers refine our understanding of this remarkable object. Ultimately, the study of supermassive black holes is intrinsically linked to our understanding of galaxy formation and evolution. These behemoths aren't just passive observers. They actively shape their surroundings, influencing the formation of stars and the overall structure of galaxies. As we continue to probe the heart of our Milky Way and the centers of other galaxies, we're uncovering a complex and fascinating story. a story of gravitational collapse, accretion, and cosmic growth, playing out across billions of years. And as technology advances, we can expect even more profound discoveries about these enigmatic objects. The Milky Way, our home, isn't just a swirling disk of stars. It's a vast, complex place, and beyond the bright, densely packed stars of the galactic plane, a much quieter and remarkably diffuse realm exists, the galactic halo. For millennia, astronomers simply observed that there were faint, diffuse stars scattered around the visible galaxy. But now, thanks to increasingly sensitive instruments and sophisticated simulations, we're beginning to understand that these stars weren't just randomly floating. They were, in large part, the product of a long, ongoing process driven by stellar winds. Stellar winds are essentially streams of charged particles, mostly hydrogen and helium ions, ejected from stars. They're not like the dramatic, explosive events of a supernova, although some massive stars do produce particularly intense winds. Instead, they're a continuous outflow, a gentle but persistent breeze emanating from nearly every star. A young, hot, and luminous star, particularly a massive one, generates a strong stellar wind. These winds carry away a significant portion of the star's mass over billions of years, gradually stripping away its outer layers. The energy of the wind isn't just pressure, it's a fundamental property of the star itself. The hotter the star, the more energetic its wind. The process begins with the star's own magnetic field, generated by the movement of charged particles within its interior. This magnetic field acts like a huge, invisible fan, channeling the outward flow of particles. As the stellar wind rushes outwards, it interacts with the surrounding interstellar medium, the tenuous gas and dust that fills the space between the stars. This interaction is crucial. The stellar wind pushes against this medium, compressing it in some areas and heating it up in others. This interaction isn't static. It's a dynamic dance of compression and expansion. Now, let's consider the sheer number of stars contributing to this phenomenon. The Milky Way contains hundreds of billions of stars, and a surprisingly large percentage of them are massive enough to produce significant stellar winds. Red giants, for instance, though nearing the end of their lives, still possess considerable energy output and generate substantial winds. These winds, when combined across the galaxy, create a truly immense outflow. But how does this outflow actually shape the galactic halo? The answer lies in the way the stellar winds interact with the dark matter that dominates the halo's mass. Dark matter, as we've explored in previous parts, doesn't interact with light, making it invisible to our telescopes. However, its gravitational influence is undeniable. The stellar winds, moving at incredibly high speeds, often reaching tens of thousands of kilometers per second, repeatedly encounter and compress regions of this dark matter. This compression isn't just a gentle nudge. It's a powerful, repeated jostling that slowly, over cosmic timescales, converts diffuse dark matter into a more concentrated, denser form. Think of it like repeatedly stirring a bowl of sand. At first, the sand is spread evenly, but as you stir, the grains begin to clump together, forming larger and larger piles. The stellar winds are performing a similar function on a much grander scale, using the gravitational attraction of dark matter as the glue to bind the compressed material. This process is believed to be the primary mechanism for the formation of dense stellar streams, elongated concentrations of stars that orbit the Milky Way in distorted paths. Furthermore, the stellar winds aren't just shaping dark matter, they're also enriching the interstellar medium with heavier elements. As massive stars burn through their fuel, they fuse lighter elements into heavier ones, eventually producing elements like oxygen, carbon, and nitrogen. These newly created elements are then released into the surrounding space through stellar winds, and eventually through supernova explosions. This stellar pollution, as it's sometimes called, gradually alters the composition of the interstellar medium, providing the raw materials for the formation of future generations of stars and planets. The stars within the halo aren't just randomly scattered. They're distributed in a way that reflects this ongoing process. They tend to cluster along the orbits of these streams, the gravitational remnants of disrupted dwarf galaxies that have been cannibalized by the Milky Way. The stellar winds are responsible for maintaining these streams, constantly pushing and shaping them as they interact with the galaxy's gravitational field. The density of the halo isn't uniform. It varies depending on the history of stellar winds and the interactions with dark matter. Scientists use computer simulations to model this complex interplay. These simulations allow them to track the movement of stars, the distribution of dark matter, and the effects of stellar winds. These models aren't perfect, of course. They're based on our current understanding of physics and are constantly being refined as we gather more observational data. However, they're providing increasingly detailed insights into the formation and evolution of the galactic halo. Looking ahead, future observations from telescopes like the James Webb Space Telescope and the Extremely Large Telescope will undoubtedly shed even more light on this fascinating process. By precisely measuring the velocities and positions of stars in the halo, and by studying the composition of the interstellar medium, scientists hope to gain a truly comprehensive understanding of how stellar winds are shaping our galaxy's vast, diffuse outer regions. It's a reminder that even the most subtle outflows can have profound impacts on the architecture of a galaxy, a testament to the power of continuous, gentle forces acting over billions of years. The vastness of the Milky Way isn't just about the sprawling disk of stars we see, or the gentle gravity that holds everything together. It's a place in constant, slow change, a cosmic history written in the very gas and dust that swirl within it. This isn't a story of dramatic explosions or rapid transformations. Instead, it's a tale of gradual enrichment, a process called chemical evolution. For billions of years, the interstellar medium, that's the space between the stars, was primarily composed of hydrogen and helium, the leftovers from the Big Bang. But this pristine mix wasn't sustainable. Stars, as we know, are incredible factories, and they were steadily transforming the interstellar medium, adding heavier elements, one star at a time. The initial steps in this evolution were driven by the oldest, most massive stars, These giants, known as population II stars, formed relatively early in the Milky Way's history. They lived fast and died spectacularly, collapsing at the end of their lives into supernova explosions. These weren't gentle fading events. They were cataclysmic releases of energy and heavy elements. A star like a red supergiant nearing the end of its life would suddenly shed its outer layers, forming a planetary nebula, a beautiful, expanding shell of gas, before ultimately becoming a core-collapse supernova. This supernova explosion wasn't just a violent death, it was a cosmic enrichment event. The intense heat and pressure during the explosion forged elements heavier than helium, from carbon and oxygen to neon and magnesium, and scattered them throughout the surrounding interstellar medium. These newly synthesized elements weren't evenly distributed. They were concentrated in the expanding shockwaves following the explosion. The key here is that these supernovae weren't just creating heavier elements. They were dispersing them into areas that hadn't yet been exposed to this process. The interstellar medium, initially filled with only hydrogen and helium, began to accumulate this stardust. The distribution wasn't uniform, however. The shockwaves from the supernovae created dense clumps of gas and dust, sometimes compressing them and triggering new star formation within those clumps. This cycle of supernova explosion, shockwave creation, and subsequent star birth was a crucial component of the Milky Way's chemical evolution. It's like shaking a box of colorful building blocks. Initially, you have only a few colors, but with each shake, more colors are dispersed and mixed together, gradually creating a more diverse palette. As generations of stars exploded, the interstellar medium became increasingly enriched. But it didn't just depend on supernovae. Lower mass stars, known as population I stars, the stars like our Sun, also played a significant role, though a more subtle one. These stars, during their main sequence lives, slowly fuse hydrogen into helium in their cores. However, they also produce a small amount of heavier elements, primarily carbon and nitrogen, through a process called the CNO cycle. These elements were released into the interstellar medium through stellar winds, streams of charged particles flowing from the star's surface. These stellar winds were less powerful than the shocks from supernovae, but they were continuous, gradually adding to the overall chemical inventory. Furthermore, the dust grains themselves were important. These tiny particles, composed of silicates, carbon, and iron, formed within the hot, dense regions of the interstellar medium. They acted as catalysts, accelerating the chemical reactions between the gas molecules. For example, dust grains could facilitate the formation of molecules like carbon monoxide (CO) and water (H2O), which are now abundant in the Milky Way. These molecules, in turn, could further contribute to the creation of more complex molecules, like ammonia and methanol. The dust wasn't just a passive carrier of elements. It actively participated in the chemical reactions. It's similar to how a chef uses a mixing bowl and utensils to combine ingredients. The bowl and utensils enable the ingredients to interact and transform. Over billions of years, this cycle repeated itself, with each generation of stars building upon the chemical legacy of the previous one. The interstellar medium became richer and richer in heavier elements. This process created population III stars, the first generation of stars in the universe, almost entirely composed of hydrogen and helium. The current population of stars in the Milky Way, including our Sun, are direct descendants of population II and population I stars, which themselves evolved from earlier, more primitive generations. The abundance of elements like oxygen, iron, and magnesium, elements vital for life as we know it, is a direct consequence of this long, slow chemical evolution. The current chemical composition of the interstellar medium within the Milky Way's disk reflects this history. It's a testament to the enduring power of stars to transform their environment. Scientists study the chemical composition of distant gas clouds, the raw materials for future star formation, to understand this evolutionary process. By analyzing the types and amounts of elements present, they can reconstruct the Milky Way's past, determining when and how different elements were created and distributed. It's a complex puzzle, pieced together through careful observation and theoretical modeling. Ultimately, the chemical evolution of the Milky Way's gas and dust tells a story of creation and transformation, a grand cosmic narrative spanning billions of years and continuing to unfold even now. The Milky Way isn't a solitary island in the cosmos, a perfectly formed spiral arm gracefully spinning through space. It's a bustling, messy, and surprisingly intimate neighborhood, and one of its most fascinating neighbors is a tiny, but immensely important galaxy called the Sagittarius Dwarf Spheroidal Galaxy. This galaxy isn't a bright, dazzling showstopper like Andromeda. Instead, it's a faint, diffuse collection of stars and gas, slowly being stretched and distorted by the Milky Way's gravity. Its story is primarily one of relentless tidal interaction, a dance of destruction and reformation, a beautiful, albeit unsettling, demonstration of how galaxies evolve. The Sagittarius Dwarf Spheroidal Galaxy formed perhaps 2.5 billion years ago, likely through the accretion of smaller galaxies, or perhaps even as a primordial companion to the Milky Way. It initially possessed a more distinct shape, a spherical form typical of dwarf galaxies. However, it wasn't immune to the pull of our galaxy's immense mass. The Milky Way's gravity is a powerful force, far exceeding that of any individual star or even smaller galaxy. This gravitational influence begins to exert a slow, steady pressure on Sagittarius. This pressure doesn't cause a sudden collision. Instead, it initiates a process known as tidal stripping. The gravitational forces are strongest near the edges of Sagittarius, pulling at the outer stars and gas. As these stars are drawn closer to the Milky Way, they don't simply fall in. They are stretched and distorted. This stretching is what we observe as tidal streams, long, wispy filaments of stars extending outwards from the Milky Way's disk. These streams aren't bright because the stars within them are relatively faint and spread out. They're incredibly subtle, representing the remnants of a galaxy being dismantled. What's particularly interesting is that Sagittarius doesn't just disappear. The tidal forces effectively tear apart the galaxy, but the material, primarily the stars and gas, remains bound to the Milky Way. These disrupted stars aren't randomly scattered. They follow specific orbital paths, tracing out elongated streams that loop around the Milky Way's disk. Scientists have identified at least 5 distinct streams associated with Sagittarius, each with its own characteristic shape and velocity. The streams aren't static. They're constantly being influenced by the Milky Way's rotation and gravitational field, shifting and changing over time. The study of these streams provides a remarkable window into the Milky Way's own formation. By analyzing the motions and compositions of the stars within these streams, astronomers can gain valuable insights into the Milky Way's past. The stellar populations within the streams are markedly different from those found in the main disk of the Milky Way. They are older, with a higher metallicity, meaning they contain heavier elements than primarily hydrogen and helium. This suggests that the material that formed these streams was once part of the Milky Way's halo, likely stripped away during earlier interactions with smaller galaxies. Furthermore, the distribution of these streams isn't uniform. They're concentrated in specific regions around the Milky Way's disk, particularly in the Perseus arm and the Sagittarius stream. This concentration of streams indicates that the Milky Way has undergone several significant gravitational encounters with smaller galaxies over billions of years. Each encounter leaves its mark, creating these elongated trails of disrupted stars. It's like a cosmic game of tag, with Sagittarius constantly being tagged by the Milky Way's gravity. The ongoing interaction with Sagittarius is also thought to be influencing the formation of stellar clusters within the Milky Way's disk. Some young star clusters appear to have been formed through the merger of streams originating from Sagittarius. These mergers create conditions favorable for star formation, as the compression of gas and dust can trigger the collapse of molecular clouds and the birth of new stars. Scientists use sophisticated computer simulation to model these gravitational interactions. These simulations take into account the Milky Way's mass distribution, rotation, and the gravitational influence of Sagittarius. The simulations help to explain the observed properties of the stellar streams and to predict how the interaction will continue to evolve in the future. It's a complex, multi-layered puzzle, and astronomers are continually refining their models as they gather more observational data. The future of Sagittarius within the Milky Way remains uncertain. It's expected to continue to be tidally disrupted, gradually losing more and more of its mass. Eventually, it will likely be completely consumed by the Milky Way, with its stars becoming just another component of our galaxy's overall stellar population. But until that happens, Sagittarius provides an invaluable opportunity to study the dynamics of galaxy interactions and to understand the complex evolutionary processes that shape galaxies like the Milky Way. It's a gentle reminder that even the grandest structures in the universe are subject to the quiet, persistent force of gravity, creating a beautiful and endlessly fascinating cosmic dance. The Milky Way, as we've explored, isn't simply a beautiful swirl of stars. It's a complex, dynamic system, a cosmic dance governed by gravity. We've seen how the gentle pressure of stellar winds sculpted the vast halo surrounding our galaxy, how the slow, methodical enrichment of interstellar gas provided the building blocks for new generations of stars, and how the gravitational tug-of-war with the Sagittarius dwarf galaxy subtly reshaped our galactic neighborhood. But there's a fundamental ingredient, something incredibly abundant yet unseen, that truly dictates the motions of the stars within the Milky Way, dark matter. For decades, astronomers were puzzled by a peculiar observation: the rotation of the Milky Way's spiral arms. As stars orbit the galactic center, we'd expect their orbital speeds to decrease with distance, much like planets in our solar system. The inner planets move faster than the outer planets. This follows Kepler's laws, a cornerstone of our understanding of planetary motion. The further a star is from the galactic center, the slower it should be moving, according to the visible mass we could detect: the stars themselves, the gas clouds, and the dust. However, when astronomers meticulously measured the orbital speeds of stars in various parts of the galaxy, they found something astonishing. The speeds remained remarkably constant, even at distances where the visible matter was incredibly sparse. Stars far out in the spiral arms were orbiting just as quickly as those closer in, as if they were being propelled by an invisible hand. This contradicted everything we thought we knew about gravity and mass. If the only mass contributing to the galaxy's gravitational pull was what we could see, the stars and gas, the outer stars should have been flung out into intergalactic space. The discrepancy was so significant that it demanded a radical solution. Scientists realized that there must be a substantial amount of unseen mass, a mass that interacted with gravity but didn't emit, absorb, or reflect light. This unseen substance was dubbed dark matter, and it quickly became the most compelling explanation for the flat rotation curve of the Milky Way. The concept of dark matter wasn't born overnight. Early suggestions arose in the 1930s, but it wasn't until the 1970s, thanks to the work of Vera Rubin and Kent Ford, that the evidence became truly compelling. Rubin, a brilliant young astronomer, meticulously studied the velocities of stars in the spiral arms of the Andromeda Galaxy, our galactic neighbor, which was then being considered a potential future merger partner for the Milky Way. Her data mirrored the findings in the Milky Way. The outer stars were rotating far too fast for the amount of visible matter present. Rubin's careful measurements provided the strongest evidence yet for the existence of dark matter, demonstrating its gravitational influence on stellar motions. The prevailing theory is that dark matter exists in vast, diffuse halos surrounding galaxies. These halos aren't made of ordinary matter. They're composed of weakly interacting massive particles, WIMPs. WIMPs are hypothetical particles that don't interact with light or ordinary matter except through gravity. The exact nature of WIMPs remains one of the biggest unsolved mysteries in modern physics, but the search for them is intensely active. Simulations of galaxy formation support the idea of dark matter halos. In the early universe, tiny fluctuations in density acted as seeds for gravitational collapse. Dark matter, because it doesn't interact with light, could collapse much earlier than ordinary matter, forming these initial halos. Ordinary matter then fell into these pre-existing dark matter structures, eventually forming galaxies like our own. Without dark matter providing this initial gravitational scaffolding, the universe would look dramatically different, far smoother and less structured than what we observe. Furthermore, observations of galaxy clusters, collections of galaxies bound together by gravity, provide additional evidence for dark matter. The velocities of galaxies within these clusters are also far too high to be accounted for by the visible mass. The gravitational pull of dark matter is what holds these clusters together, preventing them from flying apart. The distribution of dark matter isn't uniform. Simulations suggest it's concentrated in filaments, long, thread-like structures that connect galaxies across the universe, and in denser clumps around galaxies themselves. These structures aren't directly observable, but their gravitational effects are. Mapping the dark matter distribution is a complex undertaking, involving the analysis of galaxy rotation curves, gravitational lensing, the bending of light by gravity, and the movements of galaxies within galaxy clusters. The search for dark matter continues, with experiments ranging from underground detectors searching for WIMP interactions to space-based telescopes mapping the distribution of dark matter across the cosmos. It's a truly remarkable puzzle, a fundamental component of our universe that we can't see but whose influence is undeniable. The flat rotation curve of the Milky Way serves as a constant reminder of this unseen force, guiding our exploration of the deepest secrets of the universe. Far out in the darkness of our galactic neighborhood, a fascinating trio of objects dances a complex ballet around the Milky Way. These are the Magellanic Clouds, the Large Magellanic Cloud, or LMC, and the Small Magellanic Cloud, or SMC, and they hold secrets about the very birth and evolution of our galaxy. They aren't simply flung aside remnants. Instead, they represent a crucial stage in the Milky Way's history, a stage that continues to unfold before our very eyes. The origins of these clouds are tied to the formation of our own galaxy, some 10 to 12 billion years ago. The Milky Way wasn't born in isolation. It started as a denser region of matter in the early universe, a swirling disk of gas and dust. As this disk began to collapse under its own gravity, it started to attract smaller clumps of material, dwarf galaxies, like tiny magnets. These smaller galaxies, initially relatively isolated, weren't entirely destroyed. They became gravitationally bound to the growing Milky Way, forming a chaotic, overlapping system. The LMC and SMC are believed to be two of these captured dwarf galaxies, likely remnants of a population of dwarf galaxies that were prevalent during the Milky Way's infancy. What makes these clouds particularly interesting is their composition. They are remarkably metal-rich, meaning they contain a higher proportion of elements heavier than hydrogen and helium. These heavier elements, known as metals by astronomers, are forged within the hearts of stars during their lifetimes, and then dispersed into space when those stars die. The LMC and SMC are effectively cosmic recycling centers, having accumulated vast amounts of these stellar remnants. This high metallicity distinguishes them from the bulk of the Milky Way's disk, which is relatively poor in heavier elements. The extreme metallicity of the Magellanic Clouds strongly supports the idea that they represent early, highly evolved star systems. Essentially, the first generation of stars to have formed in our local galactic neighborhood. Their proximity to the Milky Way allows us to observe this evolution in a way that wouldn't be possible for most galaxies, which are often incredibly distant. The tidal forces exerted by the Milky Way's gravity are constantly pulling on the Magellanic Clouds, distorting their shapes into elongated streams and shells. These distortions aren't merely aesthetic. They are direct evidence of the ongoing interaction. The LMC, being slightly larger and closer, is experiencing these forces most dramatically. The SMC, smaller and farther away, is less affected, exhibiting a more subtle, yet nonetheless significant deformation. The most visually striking feature of the LMC is the Carina Nebula, a massive star-forming region located within the cloud. This nebula is not a single structure, but rather a complex network of gas and dust where new stars are constantly being born. The intense ultraviolet radiation from these young, hot stars is ionizing the surrounding gas, creating the beautiful, iridescent colors we see in images. The interaction with the Milky Way's disk is fueling this star formation, providing a constant supply of material for new stars to condense from. The SMC, on the other hand, boasts a distinctly different type of star formation. Its star formation is primarily driven by tidal interactions, rather than the intense radiation from massive stars. The stretching and distortion of the cloud's gas by the Milky Way's gravity is triggering the collapse of dense clumps of gas, leading to the birth of new generations of stars. Looking ahead, the future of the Magellanic Clouds and their interaction with the Milky Way is far from static. The LMC is predicted to eventually collide with the Milky Way's disk. While a complete merger isn't anticipated, the LMC will be significantly disrupted, its stars pulled into the Milky Way's rotation. This event is predicted to occur within the next few billion years, a fascinating testament to the dynamism of our galactic environment. The SMC's fate is somewhat less certain. It's likely to experience a more gradual disruption, with its stars slowly being drawn into the Milky Way's sphere of influence. However, the SMC will continue to play a crucial role in the ongoing chemical evolution of our galaxy, continuing to contribute its enriched stellar material. Scientists are meticulously studying the Magellanic Clouds, using telescopes across the electromagnetic spectrum, from radio waves to visible light, to unravel the mysteries of their origins and their future. Detailed observations of the clouds, stellar populations, their chemical composition, and their movements are providing valuable insights into the processes that shaped the Milky Way and continue to shape it today. It's a story written in starlight, a silent epic unfolding across billions of years, a reminder that even in the vastness of space, our own galaxy has a rich and dynamic history, and that we are, in a very real sense, a product of its evolution. The Milky Way, as we've come to understand it, isn't just a swirling cloud of gas and dust. It's far more complex, layered with a fascinating story written in the very building blocks of stars, heavy elements. These elements, unlike the hydrogen and helium that make up the vast majority of the galaxy, are forged in the hearts of stars and scattered across space when those stars die. Their presence, and how unevenly they are spread, provides a crucial map of the galaxy's past and a window into how it formed. Initially, the universe after the Big Bang was primarily composed of hydrogen and helium, created during the initial moments of expansion. But stars, those brilliant furnaces, are remarkable factories. Through nuclear fusion, the process where lighter elements combine to form heavier ones, they produce carbon, oxygen, nitrogen, and a host of other elements. Massive, short-lived stars are especially efficient in this process, creating incredibly rich concentrations of these heavier elements. When these stars explode as supernovas, they unleash this material back into the interstellar medium, seeding it with the products of stellar evolution. Smaller, long-lived stars also contribute, though at a slower rate. Scientists determine the abundance of these elements in different regions of the galaxy by analyzing the light emitted by distant stars and gas clouds. This is done using spectroscopy, essentially, breaking the light into its component colors, just like a prism separates sunlight into a rainbow. The specific wavelengths of light absorbed or emitted by an element appear as dark lines against the continuous spectrum, revealing its presence and concentration. The strength of these lines directly relates to how much of that element is present. What's truly remarkable is the discovery that the distribution of these heavy elements, what astronomers call metallicity, varies dramatically across the Milky Way. The galaxy isn't uniformly sprinkled with these elements. Instead, there's a clear gradient. Metallicity tends to be higher in the galactic disk, particularly in the spiral arms, and decreases dramatically towards the galactic halo. This suggests a very specific process was at play during the galaxy's formation. The galactic disk, the flattened region where our solar system resides, is remarkably rich in heavy elements. This is because it's the site of ongoing star formation. Younger, massive stars are born here, fueled by gas enriched with the material from previous stellar generations. These newly formed stars then contribute to the metallicity of the surrounding interstellar medium. It's a continuous cycle of star formation and enrichment. However, the halo, the spherical region surrounding the disk, is significantly poorer in heavy elements. This is primarily due to the halo's origin. The prevailing theory suggests that the halo formed largely from the debris of the Milky Way's first stars, population III stars, which were incredibly massive and short-lived. These stars, born in the very early universe, would have been almost entirely composed of hydrogen and helium. They burned through their fuel incredibly quickly, producing very little heavier element material before exploding as supernovas. The debris from these early supernovas, depleted in heavier elements, seeded the halo. Furthermore, the halo contains a large number of old, population II stars that have survived for billions of years without significant star formation. These stars, formed in the early universe, represent the oldest, most metal-poor populations within the Milky Way. Their light, having traveled vast distances, provides a direct glimpse into the conditions that existed when the galaxy was just a few billion years old. The distribution of metallicity isn't just a random scattering. It's closely tied to the formation of spiral arms. Spiral arms are regions of enhanced star formation, and consequently, higher metallicity. The gravitational interactions between the Milky Way and smaller galaxies, like the Sagittarius dwarf spheroidal galaxy, disrupt the disk, triggering this enhanced star formation. These interactions effectively stir the gas, concentrating it and leading to a localized increase in metallicity. Scientists use the metallicity gradients to study the Milky Way's merger history. By analyzing the distribution of elements, they can infer how many smaller galaxies have collided and merged with the Milky Way over billions of years. Each merger brings in gas from these smaller galaxies, which is then enriched with heavy elements, further contributing to the overall metallicity distribution. It's like piecing together a cosmic puzzle, where each element provides a clue to the galaxy's complex past. The metal content of our own solar system, a surprisingly metal-rich environment compared to many other regions of the Milky Way, is likely a result of the Milky Way's early mergers. The solar system formed within a region of the disk that had already been significantly enriched by the material from these smaller galaxies. This suggests that the conditions in our local neighborhood were shaped by the galaxy's turbulent history. Ultimately, the study of metallicity distribution is a powerful tool for understanding the formation and evolution of the Milky Way. It's a testament to the fact that galaxies aren't just passive collections of stars. They're dynamic systems, constantly interacting and evolving, leaving behind a rich record of their history in the form of the elements they contain. And as astronomers continue to refine their observations and develop new techniques, our understanding of this cosmic record will undoubtedly deepen, revealing even more about the magnificent story of the Milky Way. The Milky Way, our swirling home, is a place of incredible diversity, and tucked away amongst the spiral arms reside objects of extraordinary age and beauty, globular clusters. These ancient collections of stars aren't like the open clusters we've discussed, which are born and live relatively short, vibrant lives. Globular clusters are profoundly different, representing some of the very first stellar populations formed in the universe. Their existence offers a crucial window into the early history of our galaxy, and their movements within the Milky Way paint a fascinating picture of how galaxies assemble and evolve. These clusters are essentially giant spheres, often containing hundreds of thousands or even millions of stars. They're remarkably uniform in their overall density, unlike the more chaotic appearance of open clusters. The stars within a globular cluster are tightly bound together by gravity, a far stronger force than the pressure that causes stars in open clusters to scatter. The remarkable thing is that these clusters have maintained this tight grouping for an astonishingly long time, potentially since the universe was just a few 100 million years old. That's significantly older than the Milky Way itself, which is only about 13.6 billion years old. Scientists believe that globular clusters formed in the densest regions of the early universe during the epoch of hierarchical galaxy formation. As smaller clumps of gas and dark matter collapsed under their own gravity, they created potential sites for globular cluster formation. These initial clumps were incredibly rich in heavy elements, a consequence of the first generations of stars already having fused hydrogen into helium, and in some cases, heavier elements through a process called supernovae. These supernovae were incredibly powerful, scattering these newly created elements across the surrounding space, seeding the next generation of stars. The abundance of these heavier elements within globular clusters is therefore a key indicator of their age and origin. The dynamics of globular clusters are governed primarily by their gravitational interactions. Because they are so dense and have a relatively small range of stellar masses, dominated by older, cooler stars, their motions aren't chaotic like the swirling arms of the Milky Way. Instead, they follow a predictable, almost ballet-like path. The stars within a globular cluster orbit the galactic center at a slow, stately pace. Their orbital speeds are much lower than those of the stars in the spiral arms, reflecting their ancient origins and the gradual, slow processes of galactic accretion. However, these slow orbits aren't entirely undisturbed. The Milky Way isn't a perfectly peaceful environment. The gravitational influence of the Sagittarius dwarf spheroidal galaxy, a smaller galaxy that has repeatedly passed through the Milky Way's halo, has dramatically affected the paths of many globular clusters. This interaction has caused the clusters to stir and change their orbits, sometimes even stripping them of their stars. We observe this stirring through measurements of the stars' velocities within the clusters and how these velocities change over time. Studying the kinematics, the measurement of motion of globular clusters, is therefore a crucial way to understand the Milky Way's past encounters. The way in which a globular cluster's velocity changes over time tells us about the gravitational forces it's experiencing, and thus, about the structure of the Milky Way's halo, the diffuse, spherical region surrounding the galactic disk. For instance, clusters that exhibit a sudden increase in velocity might indicate a recent passage through a dense region of dark matter, or a particularly strong gravitational interaction with a passing galaxy. Furthermore, the distribution of globular clusters within the Milky Way's halo isn't random. They tend to cluster around the galactic center, forming a dense halo of their own. This suggests that many globular clusters originated from smaller galaxies that were accreted by the Milky Way over billions of years, a process known as hierarchical merging. These early mergers were essential in shaping the Milky Way's structure and distribution of mass. Some globular clusters, particularly those found in the very densest regions of the halo, have been identified as segregations. These are clusters that appear to be enriched in heavier elements than most other globular clusters. This suggests that they formed in the very first galaxies that merged with the Milky Way, representing a snapshot of the primordial universe. Analyzing the chemical compositions of these segregation clusters allows astronomers to probe the conditions that existed in the early universe. The study of globular clusters isn't just about understanding the Milky Way's past. It's also providing insights into the formation and evolution of other galaxies. Globular clusters are found in almost all large galaxies, and their properties, their abundance, their distribution, and their kinematics can be used to infer the history of those galaxies. By comparing the properties of globular clusters in different galaxies, astronomers can test models of galaxy formation and evolution. Looking ahead, ongoing research utilizing techniques like Gaia, a European Space Agency mission designed to chart the positions and motions of billions of stars, is refining our understanding of globular cluster dynamics with unprecedented precision. Gaia's detailed measurements are allowing scientists to track the subtle changes in a globular cluster's orbit over time, revealing the complex gravitational interactions that shape the Milky Way's halo. These observations are slowly revealing a more detailed picture of the Milky Way's assembly, from its earliest beginnings to its present-day form. The quiet, stately movements of these ancient clusters, observed through careful measurements and intricate calculations, are ultimately telling a story, the story of the universe itself, a story of gravity, dark matter, and the slow, beautiful evolution of galaxies over billions of years. They stand as silent witnesses, frozen in time, offering a unique window into the cosmos's grandest narratives. The Milky Way, as we've come to understand it, isn't simply a flat, rotating disk of stars. It's a far more complex and surprisingly shaped structure, and at its heart lies a feature that dramatically alters the paths of countless stars: the galactic bar. For a long time, astronomers debated whether this bar truly existed, questioning if the observed stellar motions were simply a complex interplay of disk rotation and spiral arm influences. However, mounting evidence, gathered from observations of stellar velocities and the distribution of faint stars, has confirmed the bar's existence, a roughly cylindrical structure extending through the galaxy's central bulge. It's a fascinating anomaly, a major structural element that fundamentally changes the dynamics of the entire Milky Way. The bar's origin is still a topic of active research, but the prevailing theory suggests it formed through the merger of two smaller galaxies, a minor merger billions of years ago. Imagine two galaxies, each with their own swirling disks and burgeoning populations of stars, colliding and intertwining. The gravitational interactions would have created a significant disturbance, and the stars within the resulting composite system would have begun to settle into a flattened, elongated configuration. This process wouldn't have been a tidy, graceful merging. It would have been chaotic, involving significant amounts of stellar disruption and potentially the triggering of star formation. The bar itself isn't uniformly filled with stars. It's denser towards its center, gradually thinning out as it extends outwards, and it's populated by stars of varying ages. The stars closest to the bar's central region are generally younger, having been invigorated by the gravitational disturbances caused by the bar's motion. These young stars are often found in clusters and exhibit peculiar velocities, meaning their movements aren't perfectly aligned with the overall galactic rotation. Their orbits are significantly affected, often exhibiting a secular scattering, a long-term random movement caused by the bar's gravitational pull. This scattering isn't a simple wobble. It's a complex, ongoing process that continuously alters the paths of these stars, pushing them outwards, inwards, and sometimes even sideways. The influence of the bar extends far beyond just the young stars near its center. The bar's gravitational pull perturbs the orbits of stars throughout the entire galactic disk. It's like a giant, invisible hand gently, but persistently, nudging the orbits of stars on more circular paths, introducing a slight but measurable eccentricity, making them elliptical instead of perfectly round. This effect, known as bar-induced orbital mixing, is especially pronounced in the outer parts of the disk. Consider the stars orbiting in the disk, generally aligned with the galactic plane. Without the bar, their orbits would be primarily dictated by the galaxy's overall rotation. But the bar introduces a significant component, a gravitational force that's perpendicular to the disk's plane. This perpendicular force causes the stars to precess, meaning their orbital axes slowly rotate over time. This precession, combined with the bar's ongoing gravitational influence, leads to a complex dance of orbits, where stars are continually drawn towards and away from the bar's center. The bar's influence doesn't just affect stellar orbits. It also plays a crucial role in the formation and evolution of spiral arms. The bar acts as a kind of sculptor, channeling gas and dust into the disk, funneling it along the plane of the bar and ultimately triggering the formation of spiral arms. As gas clouds spiral inwards, compressed by the bar's gravitational forces, they become denser and hotter, eventually leading to the birth of new stars. These newly formed stars, predominantly found in the spiral arms, contribute to the arm's luminosity. Furthermore, the bar's presence creates tidal streams, elongated streams of stars that are stretched out by the gravitational forces. These streams are remnants of past mergers or disturbances and provide a direct visual link to the galaxy's turbulent history. Studying the properties of these streams, such as their velocities and orientations, allows astronomers to reconstruct the sequence of events that shaped the Milky Way. The sheer scale of the bar is impressive. It's estimated to be several thousand light-years long and several hundred light-years wide, extending through the heart of the galaxy. The density of stars within the bar is significantly higher than in the surrounding disk, creating a region of intense gravitational interactions. The bar's rotation is also remarkably fast, completing one revolution around the galactic center in just a few 100 million years, a breathtakingly swift journey. Understanding the galactic bar is key to unlocking many mysteries about the Milky Way's past and future. It's a dynamic feature, constantly interacting with the surrounding stars and gas, and its evolution will continue to shape the galaxy's structure and dynamics for billions of years to come. It's a testament to the power of gravitational interactions and the complex beauty hidden within the vastness of our own galaxy. The Milky Way, our own enormous island in the cosmic ocean, isn't just a collection of stars. It's a constantly evolving system, a swirling dance of gravity and motion. And if you listen very carefully, astronomers are learning to hear the echoes of its past, specifically, the faint whispers of stellar streams. These streams aren't made of glittering dust and gas, but of stars themselves, remnants of galaxies that have been swallowed up by our own. They're like ghostly ribbons stretching across the dark gulfs between galaxies, each carrying a piece of a long-lost story. For a long time, we thought of galaxies as isolated entities, largely independent. However, the prevailing view shifted as we gained stronger evidence of galactic cannibalism. Galaxies aren't eternal, self-contained systems. They grow and change through mergers, collisions, and overlaps with other galaxies. These events leave a lasting imprint, and one of the clearest signatures of these mergers comes in the form of stellar streams. Astronomers don't simply find these streams. They meticulously track the motions of individual stars within them. It's a painstaking process, like following a trail of breadcrumbs across an incredibly vast landscape. The key is to identify stars that aren't behaving like ordinary Milky Way stars. These stars possess peculiar orbits. They're curving and bending in ways that don't fit the neat, circular paths dictated by the Milky Way's bar. These deviations indicate they're being influenced by something outside our galaxy. The most prominent and well-studied stellar stream is the stellar halo, a diffuse, extended feature surrounding the Milky Way. But it wasn't always there. Scientists believe the halo formed gradually over billions of years, primarily through the accretion of smaller galaxies, including the Sagittarius dwarf spheroidal galaxy. This galaxy, once a distinct entity, has been repeatedly disrupted and torn apart by the Milky Way's gravity. Its stars are now scattered throughout the halo, their orbits a chaotic mix of circular and highly eccentric paths. The Sagittarius stream, the remnants of this dwarf galaxy, is particularly interesting because its stars exhibit a tidal stream signature. This refers to the stretching and distortion of stars as they approach the gravitational well of a larger galaxy. The closer a star gets to the Milky Way's central bar, the more elongated its orbit becomes, creating a stream-like pattern. By analyzing the velocities and positions of these distorted stars, scientists can determine the velocity and direction of the original Sagittarius galaxy as it approached and was eventually consumed. Another notable stream, the Palomar-New Haven stream, provides evidence of a merger with a completely different type of dwarf galaxy, a spheroidal galaxy. These galaxies, unlike spirals, lack a defined disk. They are characterized by a more amorphous, peanut-shaped structure. The stars in the Palomar-New Haven stream have unusually high metallicities, meaning they are rich in elements heavier than hydrogen and helium. This is a direct consequence of the galaxy it originated from, which likely formed in a region of the universe where these heavier elements were more abundant. The study of stellar streams is not just about identifying past mergers. It's also about understanding the timeline of the Milky Way's growth. By comparing the properties of different streams, their velocities, metallicities, and shapes, astronomers can construct a detailed history of galactic interactions. They can estimate when these mergers occurred and how frequently the Milky Way has been involved in these cosmic dances. Each stream acts as a snapshot of the galaxy it came from at a specific point in time. Furthermore, the study of streams offers insights into the physics of galaxy mergers themselves. The forces involved in these interactions are incredibly complex, involving gravitational interactions, tidal forces, and the transfer of angular momentum. The way stars are disrupted and flung outwards during a merger provides valuable data for testing and refining our models of galactic dynamics. The discovery and characterization of stellar streams have revolutionized our understanding of the Milky Way. It has moved us beyond a simplistic view of our galaxy as a solitary entity and revealed it to be a dynamic, evolving system constantly shaped by its interactions with its galactic neighbors. The faint, distorted trails of stars, the stellar streams, are a tangible record of this history, offering a unique window into the violent, beautiful processes that have shaped the cosmos. The ongoing investigation of these streams promises to unlock even more secrets about the Milky Way's past and its future. The Milky Way, as we've come to understand it, isn't simply a swirling disk of stars. It's a truly immense and surprisingly diffuse structure, and when we look out towards the dawn and dusk, we often catch a glimpse of this hidden mass. This shimmering band of light, sometimes appearing as a faint glow along the ecliptic, the path the sun takes through the sky, is known as the zodiacal cloud. It's a beautiful, ethereal effect, and its existence reveals a fundamental aspect of our galaxy, the presence of a vast, dispersed halo of dust. The zodiacal cloud isn't a single, concentrated object. Instead, it's a diffuse scattering of particles, primarily tiny grains of silicates, carbonaceous material, and iron oxides. These grains are incredibly small, ranging in size from a few micrometers to a few hundred micrometers, about the size of a grain of sand or a tiny seed. They're remnants of ancient supernovae, the explosive deaths of massive stars, and the ongoing processes of star formation. These events, occurring throughout the galaxy's history, have continuously injected material into the interstellar medium, creating this extended cloud. What creates this beautiful light we see? It's a phenomenon called scattering. Sunlight, as it travels across the vast emptiness of space, encounters these minuscule dust grains. Think of it like shining a flashlight through a cloudy day. The light doesn't travel in a straight line. It's bounced around by the water droplets. Similarly, sunlight is redirected by the dust particles in the zodiacal cloud. This scattered light then reaches our eyes, giving the cloud its characteristic brightness. The brightness of the zodiacal cloud isn't constant. It varies dramatically depending on our position relative to the sun. When the sun is behind the cloud, as it is during the winter months in the northern hemisphere, the cloud appears faintest. This is because the sunlight is traveling through the least amount of dust. Conversely, during the summer months, when the sun is in front of the cloud, the scattered light is significantly brighter, making the zodiacal cloud more prominent. This seasonal variation is a key observation that allows astronomers to understand the distribution and density of this interstellar material. The cloud's appearance is also subtly affected by the Earth's orbital path. Because the zodiacal cloud exists along the ecliptic, the plane of Earth's orbit around the Sun, Our line of sight is almost perfectly aligned with its distribution. This contributes to the consistent, elongated shape of the cloud we observe. However, slight variations in Earth's orbit, particularly the precession of the equinoxes, a slow wobble in the orientation of Earth's axis, cause minor shifts in the apparent position and brightness of the cloud over long time scales. Studying the zodiacal cloud isn't just about observing a pretty light. It provides crucial insights into the overall dust content of the Milky Way. Estimates based on the brightness of the cloud, combined with measurements of the dust's extinction, its ability to block starlight, allow astronomers to calculate the total amount of dust present in the galactic halo. These calculations are remarkably challenging because the dust isn't uniformly distributed, and its properties, size, shape, and composition vary greatly. Furthermore, the zodiacal cloud acts as a kind of cosmic antenna. The scattered sunlight interacts with the dust grains, creating polarized light that vibrates in a specific direction. Measuring the polarization of the light from the zodiacal cloud allows astronomers to probe the properties of the dust grains themselves. They can determine their shapes, sizes, and how they interact with light. This provides a window into the conditions under which the dust formed and evolved. The cloud's brightness also serves as a valuable tool for mapping the density of the interstellar medium. Regions with a higher concentration of dust will scatter more light, appearing brighter in our observations. By carefully analyzing the brightness variations, astronomers can create detailed three-dimensional maps of the density distribution within the Milky Way's galactic halo. This helps them understand the complex processes shaping the galaxy's structure and dynamics. Interestingly, the zodiacal cloud isn't unique to our galaxy. Every galaxy with a significant amount of interstellar dust, and most galaxies do, exhibits a similar effect. When we observe distant galaxies, we often see a faint, extended glow along their spiral arms, reflecting the scattered light from their own dust clouds. This provides further evidence that dust plays a fundamental role in the structure and evolution of galaxies throughout the universe. Despite its subtle appearance, the zodiacal cloud offers a tangible connection to the vast, unseen matter that permeates our galaxy. It's a beautiful reminder that the Milky Way is not simply a collection of stars, but a complex and dynamic environment filled with the remnants of ancient stellar explosions and the building blocks of new stars. It's a faint, shimmering reflection of the galaxy's immense, hidden heart. The vastness of the Milky Way, a swirling island of stars, gas, and dust, has always held a profound question for astronomers. Are we alone? For decades, the search for planets orbiting other stars, exoplanets, was largely theoretical, a beautiful mathematical prediction. But with increasingly sophisticated technology, that theoretical pursuit has blossomed into a truly remarkable global endeavor. The focus has shifted dramatically toward our own galactic neighborhood, driven by the tantalizing possibility of finding worlds remarkably similar to our own. Initially, the methods were crude, relying on the wobble method. This technique exploits the gravitational effect of orbiting planets on a star. A planet's gravity tugs subtly on its host star, creating a tiny, periodic wobble in the star's position. Detecting this wobble is extraordinarily challenging because the movement is incredibly small, often less than the diameter of an atom. Astronomers utilize telescopes like the High-Accuracy Radial Velocity Planet Searcher, HARPS, at the La Silla Observatory in Chile, which are exquisitely sensitive instruments designed precisely for this purpose. HARPS and similar instruments around the world meticulously track the movement of thousands of stars, searching for these minuscule shifts. The data is processed with complex algorithms to isolate the planetary signal from the noise generated by stellar activity and the telescope itself. Early detections were groundbreaking, confirming the existence of planets like 51 Pegasi b, a gas giant orbiting a sun-like star, which shattered the long-held belief that planets were rare. As technology progressed, astronomers developed other methods for finding exoplanets. The transit method has become perhaps the most prolific. This technique relies on observing the slight dimming of a star's light as a planet passes, or transits in front of it. Think of it like a tiny eclipse, only it happens repeatedly as the planet orbits. The Kepler Space Telescope, launched in 2009, was specifically designed to detect exoplanets using this method. Kepler surveyed a small patch of the sky, continuously monitoring the brightness of over 150,000 stars. By meticulously measuring the brightness of these stars, scientists identified thousands of exoplanet candidates. The transit method isn't just about detecting the planet itself. It also allows astronomers to determine the planet's size and orbital period. Furthermore, analyzing the shape of the light curve, the graph of brightness versus time, can reveal information about the planet's atmosphere. Another powerful technique, radial velocity, has evolved with the advent of space-based observatories like Gaia. Gaia, an astrometry mission, is creating the most detailed and accurate 3D map of our galaxy. Its unprecedented precision allows for the incredibly subtle detection of radial velocity variations in stars, particularly useful for finding smaller, rocky planets close to their stars. Gaia's data is also invaluable for refining the orbits of known exoplanets, providing more accurate models of their systems. The sheer volume of data generated by Gaia is transforming our understanding of the Milky Way's population of planets. The discovery of planets around stars in the galactic bulge, a densely packed region of our galaxy, has been particularly significant. The bulge's unique gravitational environment, shaped by past mergers and interactions, creates a complex system of stellar orbits. This has led to the identification of a surprisingly high number of planets, including some with remarkably short orbital periods, just a few days. These planets, orbiting very close to their stars, are likely to be scorching hot and composed primarily of gas. Studying these extreme systems offers a unique opportunity to understand planet formation under challenging conditions. Moreover, astronomers are now focusing on finding planets in the galactic mid-disk, a region relatively undisturbed by recent mergers. This region is believed to harbor a large population of potentially habitable worlds, planets with temperatures that could allow for liquid water on their surfaces. The search here is particularly exciting because it targets systems with characteristics more similar to our own solar system. Missions like the James Webb Space Telescope, with its infrared capabilities, are poised to revolutionize this search. Webb can analyze the light filtering through a planet's atmosphere, looking for the presence of molecules like water, methane, and carbon dioxide, potential biosignatures that could indicate the presence of life. The identification of planets orbiting stars in the Orion Spur, a relatively young and dense arm of the Milky Way, has also provided intriguing insights. This region's formation history suggests a higher concentration of young, massive stars, which in turn could lead to more frequent planet formation events. The ongoing study of these planetary systems offers a window into the early stages of planetary development within our galaxy. It's important to note that the search for exoplanets is not just about finding planets. It's about understanding how planets form and evolve in different environments within the Milky Way. By analyzing the properties of exoplanetary systems, astronomers are beginning to piece together a more complete picture of our galaxy's history and the processes that shape the diversity of planetary systems. The Milky Way, once considered solely our cosmic home, is now revealed as a bustling metropolis of planetary systems, each with its own unique story to tell. The Milky Way, as we've begun to understand, isn't a static, peaceful spiral. It's a remarkably active galaxy, constantly reshaping itself through gravitational interactions, star formation, and, most intriguingly, powerful outbursts. For a long time, astronomers noticed something very peculiar coming from the very heart of our galaxy: a gigantic, almost symmetrical pair of bubbles expanding outwards into the surrounding space. These are known as the Fermi bubbles, and their origin has puzzled and fascinated scientists for decades. They represent one of the most dramatic and energetic events ever witnessed within a galaxy, providing crucial clues about the activities occurring near the supermassive black hole at the Milky Way's core, Sagittarius A. The discovery of the Fermi bubbles, initially observed in X-ray and radio wavelengths, wasn't a gradual unveiling. It started with the serendipitous observation of increased X-ray emission from the galactic center in the late 1980s. This initial signal was later confirmed by radio observations, revealing a diffuse, extended structure. What made it so striking was the geometry: two enormous bubbles, each spanning roughly 25,000 light-years, extending outwards into the Perseus Arm, a region of the Milky Way's spiral structure. The bubbles weren't simply randomly distributed. They had a clear directional flow, primarily expanding along the plane of the galaxy, hinting at a coordinated process. The leading theory for the formation of the Fermi bubbles centers around Sagittarius A, the black hole at the Milky Way's core. This supermassive black hole, while seemingly quiescent, is a powerhouse of gravitational energy. When material, gas clouds, dust, and potentially even stars ventures too close to the black hole, it doesn't get swallowed whole. Instead, it forms a swirling accretion disk around the black hole. As the material in this disk spirals inwards, It's heated to incredibly high temperatures, reaching millions of degrees. This intense heat generates intense radiation across the electromagnetic spectrum, including X-rays and radio waves. However, the energy from the accretion disk alone isn't enough to explain the scale of the Fermi bubbles. The jets of plasma originating from the black hole, powerful streams of particles accelerated to near-light speeds, are crucial to the story. These jets are formed by the black hole's immense gravitational pull, which twists and shapes the surrounding material, creating magnetic fields. These magnetic fields then channel the material outwards, accelerating it to tremendous velocities. The jets are not uniform. They are turbulent and fragmented, with smaller jets and plumes emerging from the main structure. These powerful jets, acting like immense fountains, don't simply blast outwards. They interact with the surrounding interstellar medium, the gas and dust that fills the space between stars. When the jets collide with the interstellar gas, the gas is compressed and heated, leading to further excitation and ionization. This energized gas then emits copious amounts of radiation, particularly at radio wavelengths, creating the observed bubbles. It's like repeatedly striking a pebble in a pond. Each impact creates ripples that spread outwards. The jets are the initial strikes, and the expanding bubbles are the resulting waves. The current model suggests that the Fermi bubbles were repeatedly created and revived over a period of several million years. Initially, around 400 million years ago, Sagittarius A experienced a period of increased activity, launching powerful jets that created the first generation of bubbles. As the black hole's activity waned, the bubbles gradually dissipated, but the conditions eventually became favorable again, triggering new jets and the formation of subsequent bubbles. This cycle of jet formation, bubble creation, and dissipation likely occurred multiple times, creating the layered structure we observe today. Furthermore, the composition of the Fermi bubbles provides valuable insights. Analyses of the gas within the bubbles reveal a significant enrichment with heavy elements, elements heavier than hydrogen and helium, produced by nuclear fusion within the accretion disk, and during the violent events surrounding the black hole. These heavier elements, forged in the heart of a galactic outburst, were then dispersed throughout the Milky Way, contributing to the raw materials for future star formation. Recent observations, particularly using the Event Horizon Telescope, EHT, have provided increasingly detailed images of Sagittarius A itself. These images, showing the shadow of the black hole surrounded by a bright ring of light, confirm that the black hole is indeed the engine driving these extreme phenomena. The EHT's data also allows scientists to better understand the dynamics of the accretion disk and the jet formation process. The insights gained from these observations are refining our understanding of how supermassive black holes interact with their environments and shape the evolution of galaxies. The Fermi bubbles are not just a strange anomaly. They're a window into the extreme physics occurring at the heart of a galaxy. They demonstrate that even seemingly quiet supermassive black holes can unleash tremendous amounts of energy, influencing the surrounding space and shaping the fate of the Milky Way. They remind us that the universe is full of surprises, constantly evolving through processes both beautiful and terrifying. The Milky Way isn't just a swirling cloud of stars. It's a vastly complex and surprisingly energetic place. Beneath the visible tapestry of light, a hidden force is constantly at work: magnetic fields. These aren't the static, familiar fields around a refrigerator magnet. Instead, they're dynamic, interwoven, and profoundly influence the behavior of everything within our galaxy, from the movement of gas clouds to the formation of new stars. Scientists have been piecing together the puzzle of these galactic magnetic fields for decades, using a combination of observations and theoretical models. And while many questions remain, the picture that's emerging is breathtaking in its complexity. Initially, the idea that magnetic fields played such a significant role was largely speculative. Early observations of radio waves emitted by the Milky Way hinted at organized flows of charged particles, but it wasn't immediately clear what was driving those flows. It quickly became apparent that these flows weren't random. They seemed to follow preferred pathways, suggesting a guiding influence. This led to the hypothesis that magnetic fields were acting like invisible highways, channeling the movement of material throughout the galaxy. The method of detection itself is ingenious. Since magnetic fields don't emit light, scientists can't see them directly. Instead, they observe the effects of the magnetic fields on charged particles, primarily electrons and protons, that are moving through space. These particles, when interacting with the magnetic field, will spiral along curved paths, a phenomenon known as the Lorentz force. By measuring the polarization of radio waves emitted by these spiraling electrons, astronomers can map the strength and direction of the magnetic field. This technique is most effective when observing synchrotron radiation, the light produced by these spiraling charged particles. The magnetic field strength within the Milky Way isn't uniform. It varies dramatically depending on location. The galactic disk, where most of the stars reside, exhibits a relatively weak but surprisingly pervasive magnetic field, typically around 3 microteslas. That's about 1,000 times weaker than a refrigerator magnet. However, at certain key locations, the field intensifies dramatically. The galactic poles, the points where the Milky Way's rotation axis intersects the galactic plane, are regions of exceptionally strong magnetic fields, reaching tens of microteslas. These strong fields are thought to be generated by the dynamo effect, a process where the rotation of the galaxy and the turbulent motions of the gas and plasma create electrical currents, which in turn generate magnetic fields. Furthermore, the Sun's magnetic field extends far beyond our solar system, interacting with the Milky Way's magnetic fields. This interaction creates complex structures known as the Interplanetary Magnetic Field, IMF, which profoundly affects the environment near the galactic poles. The IMF, a constantly shifting field generated by the Sun's activity, is thought to be the primary driver of the intense magnetic fields observed in these regions. Researchers believe that the IMF penetrates deep into the Milky Way, influencing the dynamics of the gas clouds and contributing to the formation of new stars. Beyond the galactic poles, the distribution of magnetic fields becomes increasingly patchy and irregular. There are enormous structures called magnetic arches, vast loops of magnetic field extending for thousands of light years across. The origin of these arches is still debated, but one leading theory proposes that they are formed by the interaction of the IMF with the galactic magnetic field, creating ripples and distortions that propagate throughout the galaxy. Another possibility is that they're remnants of ancient supernova explosions, powerful events that would have generated intense magnetic fields. The magnetic fields also play a crucial role in the regulation of star formation. Dense gas clouds, the birthplaces of new stars, are often threaded by magnetic field lines. These field lines can inhibit the collapse of the cloud, preventing it from forming a single massive star. Instead, the magnetic field can channel the gas into a rotating disk, facilitating the formation of multiple, smaller stars. This process, known as magnetic braking, is thought to be particularly important in regions with strong magnetic fields, like the galactic poles. Interestingly, observations of distant quasars, incredibly bright objects powered by supermassive black holes, provide further evidence for the pervasive influence of magnetic fields. The magnetic fields around these quasars are believed to be responsible for collimating the powerful jets of material that shoot out from the black hole's poles. These jets, traveling at nearly the speed of light, are sculpted and focused by the interaction of the magnetic field with the surrounding accretion disk. Ongoing research continues to refine our understanding of these galactic magnetic fields. New, more sensitive radio telescopes, like the Square Kilometre Array (SKA), currently under construction, promise to provide unprecedented detail about the structure and dynamics of the Milky Way's magnetic field. Scientists are using sophisticated computer simulations to model the complex interplay between the magnetic fields, the gas, and the stars. The more we learn, the more we realize that the Milky Way is a truly astonishingly complex system, governed by forces far more intricate than we initially imagined. The magnetic fields are not just a background component. They are an active, dynamic force shaping the very fabric of our galaxy. The heart of the Milky Way, a region we've termed the galactic center, isn't just a swirling mass of stars. It's a place of immense, almost unimaginable energy, fueled by a phenomenon we call an active galactic nucleus, or AGN. For eons, this region was relatively quiet, a stately spiral galaxy steadily evolving. But roughly 4 billion years ago, something extraordinary began to happen, a process that fundamentally reshaped the distribution and intensity of star formation throughout our galaxy. At the very center resided Sagittarius A, the supermassive black hole, a gravitational monster so dense that not even light can escape its pull. This black hole isn't just sitting there. It's actively feeding, consuming vast amounts of gas and dust that wander too close. As this material spirals inwards, accelerated to tremendous speeds by the black hole's gravity, it begins to heat up dramatically. This isn't a gentle warming, it's a runaway process. The gas compresses, becoming hotter and denser, eventually reaching temperatures hot enough to initiate nuclear fusion, the same process that powers our sun. However, instead of producing a steady stream of energy like a star, the infalling material undergoes a chaotic, violent transformation. This incredibly hot gas, now known as a hot spot, emits enormous amounts of energy across the electromagnetic spectrum. Radio waves, infrared radiation, visible light, ultraviolet rays, and even X-rays and gamma rays. This intense emission isn't uniform. The energy released doesn't simply spread out evenly. Instead, it creates a complex web of ionization and heating within the surrounding interstellar medium. The gas clouds, vast, diffuse collections of hydrogen and helium that were previously cool and quiescent, are suddenly bombarded with this radiation. These clouds, which could have been potential cradles for new stars, are instead heated to millions of degrees Kelvin. The thermal pressure generated by this extreme heat pushes outwards, attempting to counteract the inward pull of the black hole's gravity. This outward pressure is crucial in shaping the overall dynamics of the galactic center. The effect extends far beyond the immediate vicinity of Sagittarius A. The radiation from the AGN creates vast, diffuse bubbles of hot, ionized gas extending for tens of thousands of light years. These bubbles aren't formed directly by the black hole, though the black hole's influence is undeniably at their core. They are primarily shaped by the way the radiation interacts with the interstellar medium, causing it to expand outwards. Think of it like a very energetic, three-dimensional shockwave, continually pushing against the surrounding gas. Furthermore, the intense radiation disrupts the molecular clouds, the cold, dense regions where stars are born. These molecular clouds, often hidden from our view due to their cool temperatures, are critical for star formation. The energy from the AGN breaks apart these clouds, shattering them into smaller, more manageable pieces. While this process effectively stops star formation in the immediate vicinity of the galactic center, it also has a surprising effect on star formation throughout the Milky Way. The fragmented molecular clouds, now exposed to higher temperatures and densities, become more susceptible to gravitational collapse. This means that even in regions where the AGN isn't directly radiating, the conditions are now more favorable for the formation of new stars. The energy input from the AGN acts as a catalyst, stimulating star formation in areas that might otherwise have remained dormant. It's a counterintuitive effect, destruction leading to creation. Scientists believe that a significant portion of the stars we observe today in the Milky Way formed in response to the energetic influence of Sagittarius A and its associated outflows. The patterns of star formation aren't random. The radiation from the AGN creates filaments of ionized gas, acting as highways for star formation. These filaments, sculpted by the AGN's energy, channel gas towards regions of higher density, triggering the collapse of these regions and the birth of new stars. It's a complex, dynamic interplay between gravity, radiation, and turbulence, a process that's still not fully understood, but it's a key factor in shaping the evolution of our galaxy. Moreover, the outflows generated by the AGN, jets of extremely energetic particles shooting outwards along the black hole's axis of rotation, play a significant role. These jets interact with the surrounding gas, stripping it away and injecting energy into the interstellar medium. They also compress gas clouds, further promoting star formation. The interplay between the jets and the gas they encounter creates intricate patterns of ionization and turbulence, influencing the distribution of matter and energy throughout the galaxy. Scientists are continually using observations from telescopes like the James Webb Space Telescope and the Very Large Array to study the effects of the AGN on the Milky Way star formation. By analyzing the light emitted by these ionized gas clouds and the characteristics of newly formed stars, they are piecing together the story of how this ancient, energetic phenomenon continues to shape the evolution of our galaxy. It's a testament to the interconnectedness of the universe, how a single, powerful object at the center of a galaxy can have profound and far-reaching consequences for the entire galactic community. The study of active galactic nuclei and their influence on star formation provides a fascinating window into the fundamental processes governing the evolution of galaxies. It highlights the critical role of supermassive black holes in shaping the larger structures of the universe, and demonstrates that even the most violent phenomena can contribute to the ongoing creation of new stars. As we continue to unravel the mysteries of the Milky Way, the story of Sagittarius A and its impact on star formation will undoubtedly remain a central focus, offering valuable insights into the dynamics of our own galactic home. The Milky Way, our home galaxy, isn't just a swirling collection of stars. It's a vast, ancient archive. Scientists are engaged in a remarkable endeavor called galactic archaeology, attempting to piece together the story of its formation and evolution, much like archaeologists painstakingly examine the remnants of civilizations long past. But instead of pottery shards and crumbling temples, we're examining the distribution of stars, the composition of gas clouds, and the subtle traces of past events. The key is recognizing that the galaxy hasn't remained static. It's undergone dramatic transformations, mergers with smaller galaxies, and periods of intense star formation, events that have left indelible marks on its structure. Early attempts to reconstruct the Milky Way's infancy relied heavily on observing the motions of globular clusters. These are the oldest, most tightly bound groups of stars in our galaxy, remnants of the galaxy's earliest formations. By carefully tracking their movements, astronomers discovered that they were orbiting the galactic center at a much slower pace than the stars within the main disk. This suggested that these clusters hadn't always been part of the Milky Way. Instead, they had likely been accreted, swallowed by our galaxy during its early growth. The slower orbits indicated a period when the Milky Way was smaller and less dense, a phase of rapid expansion. Furthermore, studying the chemical composition of these globular clusters provided another crucial piece of the puzzle. Globular clusters, particularly those located in the galactic halo, often possess a distinct chemical signature. A higher proportion of heavier elements like oxygen and magnesium compared to the stars in the galactic disk. This abundance of heavy elements is a direct consequence of supernovae, the explosive deaths of massive stars. These supernovae seeded the early universe with these elements, and the globular clusters, formed before heavy element synthesis became widespread, retain a higher concentration of these primordial materials. Analyzing the ratios of these elements allowed scientists to estimate the age of the clusters, and consequently, a minimum age for the Milky Way's halo. Beyond globular clusters, the study of dwarf galaxies, small, faint galaxies orbiting the Milky Way, has provided vital clues. Several dwarf galaxies, like the Sagittarius dwarf spheroidal galaxy, have been completely disrupted and assimilated into the Milky Way's halo. The remnants of these galaxies, stripped of their stars and gas, still linger around our galaxy, offering a direct glimpse into the process of galactic cannibalism. Scientists can even identify individual stars that originated in these disrupted galaxies, tracing their journeys through the Milky Way's gravitational field. These stellar fossils allow us to witness the violent encounters that shaped our galaxy. Another exciting area of investigation involves the analysis of streams, long, tenuous filaments of stars that orbit the Milky Way. These streams represent the tidal tails of galaxies that have been torn apart by gravitational interactions. The stars within these streams exhibit a range of ages and metallicities, reflecting the various epochs of star formation that occurred as the stream interacted with the Milky Way's disk. By studying the kinematics, motion, and chemical composition of stars within these streams, astronomers can determine the distance and direction of the original galaxy that was disrupted. It's like following the trail of a lost traveler, identifying where they came from based on the clues they left behind. The James Webb Space Telescope has revolutionized this field, providing unprecedented infrared observations that penetrate the dust and gas obscuring the Milky Way's core. These observations allow scientists to directly study the star formation, regions within the galaxy's disk, and identify the chemical signatures associated with these events. It's revealing a far more complex and dynamic picture of star formation than previously imagined, a process that isn't just a continuous, steady flow, but punctuated by bursts of intense activity, often triggered by collisions and interactions. Furthermore, researchers are using sophisticated computer simulations to model the Milky Way's formation and evolution. These simulations incorporate the observed properties of stars, gas, and dark matter, allowing scientists to test different scenarios and refine their understanding of the galaxy's past. These aren't just theoretical exercises. The simulations are being increasingly constrained by observational data, creating a powerful feedback loop between theory and observation. The study of the sun's own trajectory around the galactic center is also proving valuable. The sun, along with many other stars in the galactic disk, isn't simply orbiting in a perfectly circular path. Instead, it follows a slightly warped trajectory, indicative of a past merger with a smaller galaxy, a merger that occurred roughly 8 billion years ago. This provides strong evidence for the galaxy's tumultuous history and how much it has changed since its inception. Galactic archaeology is a challenging but incredibly rewarding endeavor. It's a story written not in stone, but in the movements of stars, the distribution of elements, and the echoes of long-gone cosmic events. As technology advances and new observational data becomes available, our understanding of the Milky Way's history will continue to grow, offering a deeper appreciation for the dynamic and ever-evolving nature of our home galaxy. It's a reminder that even the most familiar surroundings hold secrets waiting to be uncovered, secrets that can reveal the profound story of our place in the universe. The vastness of the Milky Way continues to hold countless secrets, and within its luminous spiral arms, a particularly vibrant and influential region has captivated astronomers for decades: the Orion Nebula Cluster, or NGC 6331. This isn't just a pretty collection of stars. It's a powerhouse of ongoing star formation, and its effects ripple outwards, shaping the surrounding interstellar environment in a way that's still being meticulously studied. Located approximately 1,343 light-years away in the constellation Orion, the nebula isn't a single, distinct cloud of gas and dust. Instead, it's a densely packed group of young, hot blue stars, a stellar cluster, born from a colossal shockwave originating from a supernova. These stars, ranging from about 1 million to 2 million years old, are incredibly luminous, emitting intense ultraviolet radiation that dramatically impacts everything around them. The story of the Orion Nebula Cluster's influence begins with a dramatic event: the death of a massive star, a Wolf-Rayet star, within the cluster itself. These stars are incredibly short-lived, burning through their fuel at an astonishing rate and ultimately ending their lives in spectacular supernovae. While many supernovae occur within galaxies, the one associated with the Orion Nebula Cluster was particularly energetic, releasing an enormous amount of kinetic energy into the surrounding interstellar medium. This energy wasn't simply dispersed. It collided with a much larger, pre-existing molecular cloud, a vast, cold and dense region of gas and dust that lay adjacent to the cluster. The impact of this collision was profound. The intense ultraviolet radiation from the newly formed hot stars within the cluster acted as a catalyst, effectively ripping apart the molecular cloud. This process is known as ionization, where the ultraviolet light stripped electrons from the atoms in the cloud, transforming it into a diffuse, ionized gas. This ionized gas, now significantly hotter and more turbulent, became a breeding ground for further star formation. It wasn't enough simply to disrupt the initial cloud. The energy imparted by the cluster's stars initiated a cascade. The turbulent, ionized gas created density fluctuations, regions of higher and lower density within the surrounding medium. These fluctuations act like seeds, drawing in more and more surrounding material through gravity. As this material collapses under its own weight, it begins to heat up, and eventually, new protostars ignite within these newly formed clumps. This is a common mechanism of star formation. Instead of a pristine, undisturbed cloud collapsing to form a single, massive star, the cluster's energy triggers multiple, smaller star-forming regions. The radiation from the Orion Nebula Cluster doesn't just trigger star formation, it also sculpts the interstellar medium itself. The intense ultraviolet beams push against the surrounding gas, creating complex, intricate structures. These structures, often referred to as ionization fronts, are like giant, glowing ripples spreading outwards from the cluster. They carve out channels and cavities within the interstellar gas, rearranging the distribution of material and influencing the overall shape of the spiral arm of the Milky Way in which the cluster resides. Scientists use observations of these ionization fronts to understand the dynamics of the interstellar medium. Furthermore, the cluster's influence extends to the composition of the gas itself. The intense radiation heats the gas, driving away lighter elements like hydrogen and helium. This process, called photoionization, leaves behind a richer abundance of heavier elements, those forged in the cores of previous generations of stars within the surrounding region. These heavier elements then become incorporated into the gas clouds that eventually give rise to the next generation of stars. It's a continuous recycling process, a cosmic feedback loop driven by the cluster's stellar activity. The Orion Nebula cluster's impact isn't limited to the immediate vicinity. The observed star formation rates in the regions surrounding the cluster are significantly higher than those predicted based on the average star formation activity in the Milky Way. This suggests that the cluster acts as a star factory, providing a concentrated source of new stars that contributes disproportionately to the galaxy's overall star formation rate. Modeling suggests that the cluster's influence may extend outwards for potentially several thousand light years. Scientists utilize various observational techniques to study this influence, including infrared and optical spectroscopy. Spectroscopy allows them to analyze the light emitted by the cluster and the surrounding gas, revealing information about their temperature, density, composition, and velocity. These observations provide a crucial window into the processes occurring within this dynamic region. Detailed mapping of the ionization fronts, combined with spectroscopic data, is allowing astronomers to build a more complete picture of how the Orion Nebula cluster shapes the Milky Way's structure and evolution. The study of the Orion Nebula cluster isn't just about understanding a single star-forming region. It's about gaining insight into the fundamental processes that govern the birth and evolution of stars throughout galaxies. It demonstrates how stellar feedback, the effects of a star's life and death on its surrounding environment, plays a critical role in shaping the large-scale structure of galaxies. The ongoing research into the Orion Nebula cluster offers a tangible demonstration of the interconnectedness within the vastness of our own Milky Way. The Milky Way, our own grand island in the cosmic ocean, has always presented a puzzle. We've meticulously charted its spiral arms, measured its rotation, and even detected the faint glow of its stellar populations. But understanding how it formed, the chaotic, explosive events that built this magnificent structure, has proven remarkably difficult. We can examine the Milky Way's distant past, of course, looking for faint echoes of early star formation, but the sheer scale of the galaxy makes observing its infancy a challenging endeavor. Instead, astronomers have turned their attention to a much smaller, but surprisingly informative, group of objects, dwarf galaxies. These tiny, gravitationally bound collections of stars, gas, and dust offer a magnified window into the conditions prevalent during the Milky Way's earliest days. These dwarf galaxies aren't just lost satellites, they're cosmic fossils. Many of them orbit the Milky Way, held captive by our galaxy's immense gravitational pull. Some, like the Sagittarius dwarf galaxy and the Canis major dwarf galaxy, have even undergone dramatic transformations, cannibalized by the Milky Way's relentless growth. Studying these interactions is like examining a complex geological record. Each collision, each tidal disruption, leaves a traceable imprint. One particularly exciting area of research involves Small Magellanic Cloud, SMC, and Large Magellanic Cloud, LMC. These two dwarf galaxies are among the closest to the Milky Way and offer unparalleled opportunities for detailed observations. The LMC, in particular, is rich in young, hot blue stars, a clear sign of recent star formation. Analyzing the chemical composition of these stars, specifically, the abundance of elements heavier than hydrogen and helium, known as metals, provides crucial clues. These abundances tell us about the environments where these stars were born, and more importantly, the conditions prevailing in the Milky Way's early halo. Scientists have discovered that many of the stars in the LMC and SMC have chemical compositions remarkably similar to those found in the Milky Way's halo. This suggests that a significant portion of the Milky Way's halo, the sparsely populated region surrounding our galaxy, originated from these very dwarf galaxies. It's a stunning realization. The material that makes up a large part of our own galaxy originated from these smaller, now disrupted, systems. However, the story doesn't end with simple accretion. The interactions between the Milky Way and these dwarf galaxies aren't gentle embraces. Tidal forces, the stretching and distortion of objects under the influence of gravity, are incredibly powerful. When a dwarf galaxy passes close to the Milky Way, it gets stretched into a long, stream-like structure known as a tidal tail. The stars within this tail are no longer bound to the original dwarf galaxy, but are instead orbiting the Milky Way. Observations of these tidal streams, such as the stellar stream known as the Monoceros Ring, provide direct evidence of the Milky Way's disruptive growth phase. Furthermore, the study of dwarf galaxies helps us understand the nature of dark matter. Dark matter, which makes up about 85% of the universe's mass, doesn't interact with light, making it invisible. However, its gravitational effects are undeniable. Dwarf galaxies are particularly sensitive to the influence of dark matter. By carefully mapping the motions of stars within dwarf galaxies, astronomers can infer the distribution of dark matter surrounding them. The research is often focused on mapping the distribution of stellar streams. These streams aren't just random collections of stars. They trace the paths of dark matter filaments, vast, invisible structures that connect galaxies across the universe. The way these streams distort and interact with dwarf galaxies is a key indicator of the underlying dark matter distribution. The shape and complexity of these streams reveal the subtle gravitational forces shaping the early Milky Way. Another intriguing area of research involves identifying dwarf galaxies that may have been primordial, meaning they formed very early in the universe, shortly after the Big Bang. These early dwarf galaxies would have been exposed to different conditions than galaxies that formed later. By studying their properties, their stellar populations, their chemical compositions, and their dark matter content, scientists can gain insights into the conditions that existed in the universe's infancy. Some dwarf galaxies, like the Willman 1 dwarf galaxy, are incredibly faint and distant, requiring the use of powerful telescopes to detect them. Their study offers a unique window into the earliest stages of galaxy formation. The ongoing exploration of dwarf galaxies isn't just about understanding the Milky Way's past. It's also informing our understanding of how galaxies form and evolve in general. The processes occurring within dwarf galaxies, mergers, tidal disruptions, and star formation, provide a valuable testing ground for theories of galaxy evolution. It's a remarkably intricate dance of gravity and matter, and by carefully studying these small, often overlooked systems, we are slowly piecing together the story of our own galaxy's grand creation. The secrets held within these faint, distant objects are still being revealed, promising even more exciting discoveries in the years to come. Determining how far away we are from the center of the Milky Way and understanding how it's actually moving has been a surprisingly complex and fascinating puzzle for astronomers. Early attempts relied heavily on observing stars that appeared to move against the backdrop of the far, far distant universe. These stars, called standard candles, are special because they have a known intrinsic brightness, how much light they actually emit. By comparing this known brightness with the amount of light we see from Earth, we can calculate their distance. It's a bit like knowing how bright a light bulb is supposed to be, and then seeing how dim it appears from across a room. You can then figure out how far away it is. The first systematic approach involved observing variable stars, particularly Cepheid variables. These stars pulsate in a regular pattern. Their brightness increases and decreases predictably. The period of this pulsation is directly linked to the star's intrinsic luminosity. A longer period means a more luminous star, and a shorter period, a dimmer one. Henrietta Leavitt, a brilliant astronomer in the early 20th century, famously discovered this relationship while studying Cepheid variables in the Magellanic Clouds, two dwarf galaxies orbiting our own. This discovery was revolutionary, providing a distance ladder, a way to measure distances to progressively farther objects. Using Cepheid variables, astronomers began to estimate the Milky Way's distance, focusing on particularly bright Cepheids within our galaxy. The initial estimates were quite rough, fluctuating significantly as techniques improved. The problem was compounded by the fact that the Milky Way itself is a swirling disk of stars, gas, and dust. This interstellar medium absorbs and scatters starlight, making it difficult to get a clear, accurate reading of the light from distant Cepheids. The light gets dimmed and smeared, complicating the measurement process. Furthermore, the very act of observing a star from Earth introduces a subtle parallax effect, a tiny shift in position due to our own movement around the Sun. As astronomical instruments became more sophisticated, particularly with the advent of larger telescopes and more precise spectrographs. The measurements improved. Spectrographs break down starlight into its component colors, allowing astronomers to determine a star's radial velocity, its speed at which it's moving towards or away from us. This is crucial because the speed at which a star is receding or approaching us influences the apparent shift in its position due to parallax. The technique of measuring proper motion is even more subtle and challenging. Proper motion refers to the actual physical movement of a star across the sky, independent of parallax. Stars aren't stationary. They are all carried along by the rotation of the Milky Way. For many years, astronomers relied on long-term observations, sometimes spanning decades, to track the movement of individual stars. This involved carefully plotting a star's position in the sky at regular intervals, recording any gradual shifts. The problem here is that the Milky Way's rotation isn't perfectly uniform. It's faster at the equator and slower at the poles. This creates complex motions. Stars aren't simply moving in one direction. They're experiencing a combination of rotation and peculiar velocities. Analyzing these motions requires enormous data sets and sophisticated statistical methods to disentangle the various effects. The motions of globular clusters, massive collections of hundreds of thousands of stars, have proven particularly valuable in this regard. Because globular clusters are thought to have formed very early in the Milky Way's history, their motions provide a snapshot of the galaxy's early dynamics. Current estimates place the Milky Way's distance from the solar system at approximately 8,000 light-years, though this number isn't completely certain. A light-year is the distance light travels in 1 year, roughly 6 trillion miles. The true distance is still subject to ongoing refinement as new data becomes available from missions like Gaia. Gaia, a European Space Agency satellite, is meticulously mapping the positions and motions of over 1 billion stars in our galaxy. It's providing an unprecedented level of detail, allowing astronomers to build a more accurate three-dimensional model of the Milky Way. Gaia's measurements are not only improving our knowledge of the Milky Way's distance, but also shedding light on its rotation. By tracking the motions of countless stars, scientists are able to map out the spiral arms of the galaxy with remarkable precision. The galaxy isn't a simple, symmetrical spiral. It's a complex, chaotic structure, and Gaia is helping us to understand this complexity. It's revealing that the Milky Way's rotation is far from uniform, with some regions rotating faster than others, and with stars experiencing a wide range of peculiar velocities, random motions that are not consistent with the galaxy's overall rotation. Furthermore, measuring the distances to satellite galaxies, like the Magellanic Clouds, helps to constrain the Milky Way's dynamics. The gravitational influence of these dwarf galaxies provides a valuable test of our models of the Milky Way's mass distribution and rotation. The journey to determine the Milky Way's precise location and movement is a testament to the dedication and ingenuity of astronomers, a continuous process of observation, analysis, and refinement. It's a reminder that even the most familiar things, like our own galaxy, are shrouded in mystery, waiting to be unveiled by the power of scientific inquiry. The Milky Way, as we've begun to understand, isn't just a swirling disk of stars and gas. It's something far more complex, a layered structure built over billions of years. And just as archaeologists meticulously examine ancient ruins to learn about past civilizations, astronomers are now engaged in a remarkable and entirely invisible endeavor: the galactic archaeology of dark matter halos. We're not digging for pottery shards or uncovering lost temples. Instead, we're searching for the faint echoes of the immense structures that surround and shape our galaxy. The initial clue came from the observation of galactic rotation curves. For years, scientists noticed a puzzling phenomenon. Stars at the outer edges of galaxies were orbiting at surprisingly high speeds. According to the laws of gravity as we understood them, based solely on the visible matter, the stars, gas, and dust, these stars should have been flung outwards, like a stone thrown in a gentle arc. Something else had to be present, providing the extra gravitational pull. The prevailing hypothesis was dark matter, and early models suggested it formed a roughly spherical halo, a vast shell of this unseen material extending far beyond the visible galaxy. But simply knowing that dark matter existed wasn't enough. Astronomers needed to understand how it was distributed. The halo wasn't uniform. It contained intricate variations, clumps, and even filaments, vast, tenuous strands of dark matter connecting galaxies across immense distances. These structures weren't randomly distributed. They followed a pattern, a sort of galactic scaffolding. These observations, primarily made using the velocities of stars and the motions of satellite galaxies, led to the concept of dark matter halos not as a single, smooth sphere, but as a complex, multi-layered landscape. One of the most groundbreaking techniques used in this galactic archaeology is gravitational lensing. Massive objects like galaxies and galaxy clusters warp the fabric of space-time itself. This warping acts like a lens, bending the light from objects behind them. By carefully analyzing the distorted images of distant galaxies, the arcs and rings created by gravitational lensing, astronomers can map the distribution of mass, including dark matter, that's causing the distortion. The degree of distortion reveals the total mass, and by combining this data with the observed velocities of galaxies, we can infer the shape and density of the dark matter halo. Furthermore, simulations have played a crucial role. Cosmologists use supercomputers to model the evolution of the universe, starting from the Big Bang and simulating the formation of galaxies and their halos. These simulations show that dark matter halos formed first, providing the gravitational seeds around which galaxies coalesced. The size and density of these halos were largely determined by the initial density fluctuations in the early universe, fluctuations that were amplified by gravity over billions of years. These simulations aren't perfect, of course, but they provide a powerful framework for interpreting observations and testing our understanding of dark matter. A particularly intriguing aspect of galactic archaeology concerns the structure of the Milky Way's own dark matter halo. Evidence suggests it's not a perfectly spherical halo, but a filamentary structure, resembling a cosmic web. This web is connected to dark matter halos of other galaxies, forming a vast, interconnected network. The Milky Way sits within one of these filaments, constantly interacting with the dark matter halos of neighboring galaxies through gravitational forces. These interactions, tidal forces, gravitational pulls, subtly influence the motions of our own galaxy and even contribute to the formation of stellar streams, elongated groups of stars that have been ripped from their parent galaxies. The study of dwarf galaxies, like the Sagittarius dwarf spheroidal galaxy, is particularly vital to this archaeological endeavor. These small, faint galaxies are frequently disrupted and consumed by the Milky Way's gravitational pull. As they orbit and interact with the larger galaxy, they shed stars and gas, creating stellar streams that provide a direct probe of the Milky Way's dark matter halo. Analyzing the velocities and orbits of these disrupted stars allows astronomers to map the density and shape of the halo with unprecedented precision. Scientists can even date the stars in these streams, determining when they were last part of a larger galaxy, offering a timeline of the Milky Way's interactions. Recent research has also focused on the cuspy nature of dark matter halos. Simulations predict that dark matter halos should be denser towards the center and gradually become more diffuse further out. However, observations of dwarf galaxies show a surprising result. The density remains relatively constant out to large distances. This discrepancy, the core cusp problem, is a significant challenge for dark matter models and highlights the complexities of galaxy formation. The investigation of the Milky Way's dark matter halo isn't just about understanding the past. It's profoundly relevant to understanding the future of our galaxy. The gravitational interactions within this halo are shaping our galaxy's evolution, influencing the formation of new stars and the distribution of gas. By continuing to meticulously map and study the dark matter halo, we gain crucial insights into the ongoing drama of galactic evolution, a drama played out on a scale that is both breathtakingly vast and profoundly intimate. It's a process of uncovering the hidden layers of a cosmic mystery, revealing the secrets of a structure that, while invisible, is undeniably the foundation upon which our own galaxy stands. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The Milky Way stretches out before you, a river of stardust, silent and ancient. Let your thoughts drift, calm and unhurried like clouds across the cosmos until sleep finds you.